So, hello, Insomnihack. Happy to see so many people in the room. I think it's because security folks love blockchain, right? How many of you are running a blockchain node or validator? Oh, not so many. Okay. Well, I guess at least you've heard of Ethereum. So as you can see, I'm alone here. My friend Denis could not make it because he lives in Tomsk in Siberia in Russia. And because of the recent event, he had to change his plans and he could not be here today. So it's called hunting for bugs in Ethereum 2.0. But if you're following closely the Ethereum news, you know that we should call it just Ethereum. The term 2.0 is obsolete. I will explain why a bit later. And more specifically, I will talk of hunting bugs in Ethereum clients. Well, clients, because as you will notice later, they're not only clients, they're more like servers, but they're called clients anyway. So the concept of this work is a grant from the Ethereum Foundation that we received jointly with Denis Kolegov and Evangelia Statopoulou from University College London. We published a paper in October that is quite long, so I will summarize it so that you don't have to read the paper. So what's Ethereum? If you've lived under a rock for the last 3 years, last 5 years, it's a blockchain platform. So what is a blockchain? I'm not going to explain it. It's a kind of database, but slower. And run by many sketchy people. But it's the future, you know. And it's the main blockchain platform as opposed to the main cryptocurrency, which arguably is Bitcoin, according to some metrics. And Ethereum is the main platform that people use to create their own tokens, such as ERC20 tokens, but they also use it to create decentralized applications, also known as dApps. And one specific class of dApps is dApps that serve for decentralized finance applications. So the alternative to a centralized exchange platform such as Kraken. In DeFi markets, it's a way to buy and sell tokens, which may or may not have some value, but where the logic is run purely on-chain via smart contract, as opposed to a centralized computer. So in the blockchain world, centralized, bad, decentralized, good. You don't need to remember. You don't need to think that much. And there's a big problem with Ethereum. As you can see here, people started complaining because Ethereum was so successful that it became quite slow and inefficient. So high gas fees. So the gas is the price you pay to send your transaction. Slow and congested. A lot of transactions fail and people lose money. It's not the future. Traditional finance is probably laughing at us. We need other blockchains, yada, yada. So Ethereum needs to do something to scale. So scale means being capable of managing more transactions. And the problem is that to manage transactions, to process transactions, you need two things. You need processing, you need computation, and you need data. Why computation? Because when you execute a smart contract, when you want to deploy a smart contract, it has to be verified on-chain. And verification usually happens by recomputing the program, which is completely waste of CPU because you have hundreds of validators. And for one single program, it has to be verified, recomputed by tons of people. And the blockchain has a database, also has to store some data. So the state, the arguments, the logic that has been executed. And so the more transactions, the more data and computation. And at some point you reach the threshold when it's not manageable. And it's quite slow indeed, 15 transactions per second. So transaction is not only a transfer of money, it's any change. So remember, it's a database. So in the database world, a transaction is a change of the state. Or read operation. So it's leading to, by a simple offer and demand, high gas fees, and to a congested network and people who are not really happy. So you see a comparison between this big computer that a lot of people are using, distributed over many computers, 600,000 additions per second. And you compare it to the small computer that only one person wants to use, like Raspberry Pi, like $40, 3 billion additions per second. That's the future. So how to scale? There's two classes of solutions. The first one is change the operating system, so to speak. That's called layer 1. Change the way Ethereum behaves. The second way is what we call layer 2. Change how the application works, or try to create another network on top of Ethereum. So that's what people call sidechains, where you create your own separate blockchain And from time to time, you commit your state into the main blockchain. That's a poor simplification of how L2 protocols work, but I think it describes the general idea. So today I will only talk of L1, layer 1 of Ethereum, and I will not cover layer 2. So the layer 1 approach to scale includes different components. That's what used to be called Ethereum 2.0. The first one is proof of stake, whereby instead of doing a lot of computations like in a proof of work, you just stake assets. So you say, oh, I have a lot of money, so I have the right to do a lot of things, and to be rewarded for it. And data sharding is, if you know database, you're familiar with sharding. Sharding is just a way to distribute the storage across multiple components in a relatively efficient way. And the main component to manage these proof of stake and sharding mechanisms is what they call the beacon chain, which was deployed in production in December 2020. So what is the beacon chain? The beacon chain, it's a network of nodes, technically, that maintain a state. So remember, it's a database. You maintain a state, and it's decentralized, distributed. So you need multiple people who work together. And because they don't trust each other, you need some complex consensus protocols to make sure that as long as the majority is honest, then the state is safe. So Ethereum described the beacon chain as follows. Imagine Ethereum is a spaceship. It's not quite ready for the interstellar voyage. You know, the thing big. With the beacon chain, the community has built a new engine and a hardened hull. When it's time, the current ship will dock with this new system, merging into one ship, ready to light years. Okay, makes no sense. Maybe in French, it's clearer. It's the official Ethereum page. Le staking. La mise en jeu. So mise en jeu is the French for proof of stake. Discovered today. L'acte de déposer 32 ETH pour activer le logiciel de validateur. Blablabla. Et ce processus, connu sous le nom de preuve d'enjeu, proof of stake, est introduit par la chaîne phare. Beacon chain, chaîne phare. Okay, I get it. And then, en savoir plus sur la chaîne de balise. What? Chaîne de balise. So they're a bit confused. They use different translation for beacon chain, chaîne de phare or chaîne de balise. I don't know which one you prefer, but. So to run the beacon chain, these nodes, they need to run some piece of software. It's called the beacon client or consensus client, but they're actually more akin to a server component, which confuses me at the beginning and still today. So these are four, Nimbus, Lighthouse, Teku, and Prism, respectively in NIM, the NIM language, not the NIM blockchain, Lighthouse in Rust, Teku in Java, and Prism in Go. In terms of popularity, so the main metric to compare popularity is GitHub stars, as everybody knows. So the most popular is Prism, 2,000 stars, then Lighthouse, 1,000, then Teku and Nimbus are a bit close with 200-300. That was, in last September. In terms of usage, Prism really dominates. You know, more than half of the nodes are Prism nodes, then Lighthouse, and then, Teku and Nimbus. So you see that kind of matches the GitHub stars. We demonstrate that GitHub stars is a good indicator again. And no surprise here. Most of the nodes are in the United States of America. So what is a beacon client? So again, it's not a client, it's a server. And it's running two main services. One called the beacon node, which is a kind of passive service that is just looking at the blockchain, at the beacon chain, and that you can query to get value, to get information on this beacon chain. You can ask the latest attestations, you can ask how the latest block looks like, this kind of thing. The validator is the most important component. It's the one that is really doing the work to actively maintain the blockchain. And the one where security really matters, because they are checking that the blocks that are submitted. So a block is essentially a proposal of a change to the database, to the blockchain. And then you sign attestations, let's say to say that, okay, from my perspective, I've done all the security checks and this block fulfills all the requirements and we can accept it. And we're going to only to accept this one because you cannot accept two blocks at the same time. So this introduces some new components because the beacon chain is quite different from the non-beacon chain. So first of all, a new type of cryptographic signatures, BLS, slashing, a punishing mechanism that I will not discuss because of time constraints and because we didn't find bug in it, and an API, and also a peer-to-peer layer. Okay. Is the sound okay? Do you hear me in the back of the room? Okay. Our methodology is very deep and scientific. Well, we're lazy like everyone. So we look at the code, we try to find bugs. And the easiest way to find bugs is to compare the specs with the code, rocket science, and even easier to compare implementations of the same thing. So even if you don't understand anything, you compare the code of two different clients. You don't know what they're doing, but they do the same thing differently. Then you ask yourself, why? Why they do these operations in different order? Why they have different parameters? And maybe that's a bug. Maybe not. So that's essentially what we did. Okay. So first, BLS signatures. Maybe you're familiar with, ECDSA, elliptic curve DSA signatures, or ED25519, all these elliptic curve digital signatures. So we're talking of asymmetric public signatures, not max. They're quite complex. You look at ECDSA, it's very complex. You pick a random value. You have to do a lot of checks, modular inverse, division, multiplication, addition, all the possible math operations to sign. And your signature is not one value, but two values. So here with BLS signatures, it's much easier. You have your message that you want to sign. You hash it. And you do one multiplication with a secret key, and that's it. So technically, this is a point. It's not a hash function like Blake2. It's a hash to curve hash function, whereby you hash a piece of data onto an elliptic curve. So the result is not a string, it's a point on a curve. And the secret key is a number, a scalar. So crypto people say scalar because it sounds more serious than a number. Who's calling me? No, I'm giving a talk, sorry. Okay, so what can go wrong here? Look at this line. Can you imagine what could be the problem? Yeah, I'm hearing the Google response. So the first thing you learn in security is validate your input and reject bad inputs. So what would be a bad input here? It would be the 0 value here. So typically you receive either the message or the hash of the message in your API. And if this value is 0, so 0 multiplied by anything is 0. So it means that you would get the same signature regardless of the value of the secret key, which means that you could forge a signature of a message without knowing the secret key. I mean, it sounds very stupid, but this 0 bug was present in many implementations. And someone wrote a paper called 0, which is annoying. When you want to Google for the paper, you Google 0. And then he did another paper called 00 because he found other bugs based on this. So this zeroness issue is one specific instance of a class of invalid values that you may receive. And you have some, so this is a pseudocode in the IETF draft that describes the core verify function, the core verify procedures to verify signature. And you have these two routine signature check, subgroup check. So you check that your point is in the right subgroup of the elliptic curve group of points, and you validate the key. So here several things can go wrong. Maybe you can just, forget to do this altogether, one of the two, or maybe you have a function that is doing it, but it's doing it incorrectly, or maybe it's doing it correctly, but you don't check the result correctly, or maybe you check the result, but then you do the bad thing. A lot of things can go wrong here. Likewise, here you look at the specs, and you look at this, like the official reference, and you say, if one thing is wrong, return invalid. Invalid, invalid, invalid. And if you see the return value, you know that it's failed. You don't know why. So just, you see an invalid. But what most implementations would do, they would return an error message or an error code that would be specific to the error, which gives you more information about what happened internally, which might potentially be used as an oracle to determine what happens inside. So I'm trying to give you, some examples of cryptographic protocol failures. So I'm not going to give details of the bugs, but it's this kind of bug that we found, and we found 90 of these bugs across all the 4 projects, and also in the specifications of Ethereum 2.0. So none of these were really exploitable in the sense that you could steal money for free. Well, otherwise we would have reported it, of course, but just happened not to find such bugs. So we reported the bugs, and what's funny in the blockchain space, oftentimes, well, some projects do have a security contact, but some people just report stuff in the GitHub issues. So yesterday, somebody told me the case of a guy who reported a bug in a GitHub issue of a project and say, oh, critical bug, you can steal millions worth of money with this bug. And the guy was so nice. And he even included a POC. So, and somebody told him, what the fuck you're doing? And he removed it. But some people do not think so much. Next step, the peer-to-peer layer. So what's great with blockchain people is that they're very smart. Well, some of them, not all of them. They have a lot of money and a lot of time. So what do you do when you have all this? You reinvent things. You do things. So they reinvented peer-to-peer secure transport protocols. And they encrypt connections between different validators. So why encrypting things? Because you want security, so you need to encrypt. But it's not just about plain text or ciphertext. It's also about authentication. So how to authenticate your parties, how to authenticate to other parties. Confidentiality, make stuff secret. Integrity, make sure that stuff hasn't been modified. Non-repudiation, making sure that if you sign something, well, no one else can sign stuff on your behalf or can modify what you signed. And a few other things. I don't know if they mention it. Yeah, perfect forward secrecy and non-replayability, anti-replay. Okay, so we looked at the P2P protocol implementation and we tried to see if these were satisfied. Spoiler, not all of them. So what do they use for peer-to-peer? They use libp2p, which was designed, I think, mainly by Protocol Labs for the IPFS, so Interplanetary File System protocol, which is really cool cryptographically. I don't know how useful it is, but cryptographically it's fantastic. They do proof of space time. It's like magic. And libp2p is not just one library. It's not just one protocol. It's a suite of protocols for secure transport, Muxer, discovery, peer routing, a lot of things that you have listed here. And it's called the de facto Web3 networking layer. And I think it's a fair description. So what is libp2p again? It's a suite of protocols. libp2p-noise is one secure transport. So think of it as kind of secure tunnel, as a kind of WireGuard or IPsec. And this one is using the noise protocol framework. And in the noise protocol framework, you have multiple flavors of noise, multiple ways of doing a handshake. So a handshake is when you initialize a cryptographic session, a cryptographic tunnel between two parties or more. And noise XX, double X, or 20, I don't know how to spell it, is a specification that happens to be used in Ethereum. Okay, so here's Jessica and Morty. They want to communicate. Well, Morty wants to communicate with Jessica, but in this case, she initiates the session. So you have three types of keys. The ephemeral key with the suffix E here. So ephemeral means that it's short-lived, just for the sake of this specific session. You have the static keys, which are here. So each party knows the static key of the other. They're more like long-term keys. So in the noise framework, the static keys are really long-term keys. But in the world of Ethereum, they're more like mid-term keys because you have another layer of keys called the identity key, which is your key that never changes. And when you want to issue a new static key, you sign the static key with your identity key. And hopefully people will verify this. Hopefully. So what happens in noise? I don't have too much time, but it goes as follows. You send an ephemeral key. Then Morty is picking a new pair of ephemeral keys, is doing different operations between a combination of Jessica's public key and his secret ephemeral key, his secret static key. Then he sends his ephemeral public key and the encryption of his static public key. You might ask why? Why? Because he can. And he can with what? With the DH1 here. So each stuff that you send here is encrypted with the key that you can generate with what you have. And then she does the same. You don't need to understand what happens. You just need to see that a lot of crypto is happening here. So three different operations, DH1, DH2, DH3. So DH1 here is the same as DH1 there, and so on for the rest. And at the end, they have three DH values, and they derive a symmetry key from it, and they can encrypt stuff with that. So ultimately, they both authenticate to each other using all these keys. So a lot of keys, a lot of crypto. Too much crypto, maybe, I don't know. What can go wrong here? If you sign your new static keys with an identity key, what kind of attack can you do? You have a secure signature scheme, you have secure keys, and you just take the key and sign it and send it. No idea. Sorry? Yes, yes. Yes, but yeah, they know your identity key, and you want to say, okay, I have a new static key. Here's a signature of it. So the risk is a replay attack, because it's not bound to the session. There's no counter, so you can take a previous signature, a previous public key. So the public key is public; it's not secret. So you can take the public key, you can take the signature, which is also public, and use it again on behalf of the person. So you don't know the secret key, you will not be able to initiate a session, but it will force the other parties to erase the other public key, and it's kind of a DOS vector. So how to fix it? You can just sign, instead of just the key, sign the key and some value that is unpredictable to an attacker. It can be a random value, a random challenge. It can be a hash of the session transcript, anything that the attacker cannot predict. Another attack vector is the following. So here, what can you exploit if you're an attacker in this part of the protocol? So Jessica is sending her public key, and Morty is doing some crypto computations. So it's again a DOS vector, because you send many public keys, and you will force Morty to do 1, 2, 3 cryptographic operations, so 2 exponentiations, and 1 key generation. And if you send thousands or more public keys, then he will use a lot of CPU. So how can you fix this? So if you look at, so it's mostly for UDP. In this case, we're working with TCP, so it's less relevant. But if you look at DTLS, at IPsec over UDP or WireGuard, they have some tricks to prevent this. So what WireGuard is doing is using what they call session cookies. If they see too many public keys coming in, they will say, wait, hold on. Take this challenge and sign it for me when you send your next public key. And if you sign it correctly, I will accept the session. So it's a kind of a trick to prevent this kind of DOS. So it's kind of rate limiting, whereby the receiver refuses to process the public keys if they receive too many of them. Okay. So one bug that we found is a simple integer overflow in the JavaScript or TypeScript library, and when we traced it back to the Go version, and this Go version, we did some advanced forensics, and we found that it came from the Noise Explorer framework, which generates automatically some implementations of noise. And here the problem is, the nonce reuse problem in crypto. If you use twice the same nonce with AES GCM or Stream Cipher, then you can potentially decrypt for free the plaintext. So here's exactly what happened. The nonce was only 64-bit. It was incremented. But then if you reach the maximum, it would wrap around and repeat again the previous values. Whereas the spec says that you should not do it because it's bad. And it was not done in the code. So they fixed it like this, and now it works. This one was from a few days ago, and it's not our bug. Quite a shame that we missed it, by the way. But it's because we suck at JavaScript. So it's much more severe. It's a man in the middle, whereby the signature verification can be completely bypassed. So before I described a replay attack, here it's even worse, not just a replay. It's a full man in the middle. Why? Because of some specificity of TypeScript. It doesn't complain about this. I don't know what it means in JavaScript. It's some promise issue, but it looks apparently quite non-trivial to spot. And well, the upshot is that the signature verification was not checked. It was accepted even when it was not valid, which is not good. Okay, now let's go to the API. So the API, it's a standard HTTP, REST, or RPC, and gRPC under the hood, the usual stuff. And since it's the usual stuff, we found the usual bugs. So the spec is saying something about how to process and not to process the HTTP headers. And most of the clients who are doing this wrong, like not looking at the headers or accepting invalid headers, this kind of thing. They will not validate the JSON schema. They will accept invalid fields in the JSON schema, this kind of thing. Sometimes the API would be publicly exposed, whereas it should be authenticated. We even found some authentication tokens written in the logs as a convenient way to access the tokens, but I don't recommend this. The logs are not secret in general, well, it depends. Also some requests that were possible without an API token, and some DOS vectors whereby you send some parameters. You send 10 bytes and you receive 100 bytes. So this kind of DOS vector. Last part, the supply chain risks. So as you know, most of the modern software projects have maybe 80% of their code written by other people because they come from dependencies, other packages. And it's very convenient because you just need to call someone else's package. You don't have to write it yourself. But the flip side is that you depend a lot on these other people and their code and their security. And maybe you have very good SDLC pipeline and CI and, all the tools you want to have, the linters and that. But these guys, you don't know what they do. You don't even know if they maintain their code at all. So there's a risk of active sabotage, malicious sabotage. It's happened in the past. Backdoors or bugdoors or possible deniability. It can be a version management nightmare because let's say you find this direct dependency that is outdated. You say, I will update it in my cargo or Go mod or whatever NPM stuff is using. But then you discover that one of your dependencies is using a dependency that is using a dependency that is using a dependency that is using the outdated version of that one. And it happens to have a vulnerability. And even if you have the latest version of the first degree dependency, if this guy did not, update all the dependencies, then there's not much you can do. You have to accept the risks, so to speak. Another point in an enterprise context can be quite annoying is the copyright and licensing issues. If you have some GPL dependency buried in your dependency graph, it might bite you at some point. So the good thing is that the last 2 or 3 years, there's been a lot of great tooling developed. For example, in NPM, you might know the NPM audit command. In Rust, the cargo audit, cargo outdated, cargo Geiger. All these fantastic tools. Go is catching up as well. And it helps you to identify easily the problems. And there are some other platforms, I think Go and GitHub also, Dependabot, all these cool tools. So I'm quite happy with this. It's making our life easier. But we wanted to have some, let's say, some indicators, some metrics of the risk for these 4 clients. So we started looking at Prism in Go. So that's an excerpt of the dependency graph. So can you see how many dependencies there are here? 403. In Rust, it's even more artistic. So just a small part, So how many dependencies? So in Lighthouse, there were 121 direct dependencies, but 440 in total when you include all the transitive dependencies. And Prism 93 direct, but 665 in total. So it's quite a lot. So we try to enumerate the outdated version and the vulnerable versions, but these numbers are not always meaningful because I know that some projects, they just update the dependencies when they're going to release a new version. So I don't think you should draw any conclusions from the outdated version and vulnerable versions here because each protocol has their own release process and update management process. So we tried to find some metrics that were meaningful for all the languages, that made some sense in terms of risk. So I don't know if they are good, but that's the best we have. We also try to see the number of CVEs. So CV is you probably know what a CVE is anyway. And in Java, surprise, a lot of CVs in Java. You don't know, it might be because in the Java ecosystem, people prefer to report CVEs. And in Rust, there is another database for vulnerabilities, and maybe people are less interested in CVs. You don't know. So there are a lot of hidden biases here. Also, what is also hard to find is more qualitative metrics in terms of which dependency you use. And I have little time, so I will talk about this. Initially, we were like, okay, let's focus on the critical dependencies. Which are the critical ones? The ones that do crypto operations, the ones that do security. These are critical. But then we realized, wait, hold on. Any dependency is code that you're running. So if I were to backdoor a project, I would not target the critical one. I would target the one that people will not look at, the one that is changing the color of the buttons, the one that is just, doing some Unicode shit, whatever. Or if I'm even more evil, I would take some dependencies that many projects are using. So it was very hard to think in terms of, okay, which dependencies should we look at? Because we cannot look at 100 projects and manually see if they are done by reputable people, if they have a good set of unit tests of SDLC. So yeah, we didn't, we gave more questions than answers, to be honest. But my conclusion of this, I know in terms of language, in terms of security, Lighthouse is doing a much better job because they have fuzzing in their CI pipeline. They do things pretty well. They have a lot of, linting, static analysis. And as far as I can tell, they have pretty smart developers. The other ones are a bit less advanced as far as I could see in security, but any project can have scary bugs, even if you have the best people on earth. So to conclude, again, we did not find high severity or critical bugs, which did not really surprise us because there was really a huge amount of, cleanup done before we came. All the project has been audited by the usual suspect companies. There's been some fuzzing done, fuzzing of the interfaces, fuzzing of the state machine, a lot of testing. So yeah, and they're doing their best. But as you know, if you have a complex system, a new system, a lot of code is the recipe for many bugs. And especially in the context of blockchain where it's decentralized, distributed, and you have bugs that you can only identify when you're running this in a production-like setting where you have multiple machines interacting in this asynchronous context, and you hit some edge case that you could not anticipate just by looking at the code. And that's what scares me a bit. And that's how many people discover some bugs. They were like, oh, our testnet is stuck. Why? And it takes them hours or days to investigate until they find the bug. But yeah, that's, the proof is in the pudding at the end of the day, because if your blockchain is running and if people can make millions if they break it, and if it's not broken, then it means that your security is at least, $5-10 million, So I think that's a good way to reason. But at the same time, there's some high incentives. If you find a critical bug, and if you're a bit, evil, you may not want to disclose it, because you can say, okay, I can make 10,000 from the bug bounty. It's clean money, but I can make 1 million by exploiting it, but it's dirty money. How does it cost to launder the money? And that's really how people reason about this. So what's the best client? Which one to choose? That's what people ask us. We have no idea. But the difference is that Lighthouse, as I said, is the most focused on security in terms of performance. CPU, disk usage, it's quite good. But Prism happens to be the most popular, so maybe because Go is easier to use, I don't know. Nimbus is designed to be lighter. I don't know if it runs a smartphone, probably not, but it's quite lighter. And Teku is more enterprise oriented. They have some commercial support if you need that. It's probably good to have some level of diversity of clients, because if you have only one single big client and if you have a bug in it, then all the clients are down. But you can argue that if you have many more clients, you have much more bugs to exploit. So you need to find the right balance. So last but not least, the question, when will Ethereum 2 be available? I have no idea. And so what Ethereum is saying, they say, a date has not been set as of the publication of this post, which was 14th of March. Any source claiming otherwise is likely to be a scam. Updates will be posted on this blog. Please stay safe. And it's funny, I looked at the French version. Do they say the same thing? Quand la fusion aura-t-elle lieu? So la fusion, the merge, is when you merge the proof of stake world with the main network of Ethereum. La fusion, donc une date n'a été arrêtée. It always sounds smarter when you read French, La preuve d'enjeu. I love this, la preuve d'enjeu. And you know how to say, I have a few minutes. We're in a call with a client, my company, a French bank, and they say, alors, comment supportez-vous les bifurcations dures? What? So, les bifurcations dures, he meant the hard fork. So, toute source qui prétend le contraire est probablement une escroquerie. Voilà. Okay, so, I hope you have fun with the preuve d'enjeu and bifurcation. Thank you.
Thank you very much, JB. I know you have a train to catch and you need to run. So do you have the time for a few questions? Or?
Yeah, I can take a few questions.
Okay. If you have any questions, please raise your hand so I can bring the microphone to you. Yeah.
So thanks for the talk. I have a question about the denial of service defense, because even if the defender asks the attacker to sign something for him to verify that it's a legitimate request, then you still need to verify the signature, and that it feels like it would take a similar amount of time to actually performing the step of the protocol.
For the DOS vector, where it's a multiple public keys, yeah, but in that case, you also force the attacker to do many computations. And they would do the same kind of computation if they sign it with a Mac. Is the same amount of CPU on the attacker's side and on the victim side.
But they can send a bogus signature, and what happens then? You just disconnect and try again.
So I think there's a good point. It does a mechanism whereby if they send too many invalid signatures, you just reject everything for some period. I think you might want to check the WireGuard implementation. I think they have quite a clever version of this.
Okay, thanks.
Yeah.
Hi. You mentioned that there's in the original protocol, there's an option for a replay attack when sending a key update. And you propose to include a random value that's not predictable by an attacker. What about using a sequence number so that you can check if it's a new one instead of an old one?
Yes, that would also work, but then you need, so either you transmit the sequence number with the value, but the other party needs to be synchronized with the same sequence number. And the problem is that if you miss some message, okay, you send the 2, the 3, you receive the 2, the 3, you don't receive the 4, and suddenly you receive the 5. You're like, okay, did I miss a message? So you need both parties to maintain a counter, and it gets more complicated. So typically it's better to be stateless in order to avoid having to maintain a shared state.
All right. Any other question?
Hi, thank you. Nice talk. So I have a question. What is the idea behind catching denial of services when you control like the beacon infrastructure? Because when they deployed proof of stake, basically they are not able to stop people to actually take over to the network. So I mean, denial of service is just you are attacking a service, but you can actually go and do a kind of transaction hijacking by controlling the beacon servers, you know?
Yeah, I think the exploitation scenarios are non-trivial, but what I did not mention is that there's also a service called the slasher service, where some validators are trying to detect invalid transaction when someone is cheating. So being able to DOS some of the nodes might help when having a collision of attackers, and you want to prevent some nodes from reporting a faulty and invalid transaction. Or you want to have an edge, for example, if you want to exploit, you know, I don't know if you're familiar with MEV attacks, where you try to exploit the early knowledge of the next transactions, and you want to force one transaction to come before another, and you collude with other parties. So especially since there are not that many validators, well still a few thousands.
But I guess you would prevent isolation of the eclipsing attack. You would prevent it, you know. I mean, otherwise the beacon network wouldn't exist.
Yeah.
So
yeah, that's the point. To have a highly connected network.
Yeah, but my question, I mean, the latent question is, who is the owner of this network? Is really decentralized, but in the end, because you have this infrastructure which is like 24/7.
supposed to be decentralized, and I think they try to have nodes validators maintained by different people, different organizations in different countries. From my perspective, it's a fair level of decentralization at this point, and even better than in some other blockchains where you have big pools of proof of work. Whereas here it's, well, to my taste, a bit more decentralized. I will not give names of blockchains, but.
All right, thank you. Any other question? Okay, so we finished a little bit earlier. We have like a little bit less than 20 minutes. So if you guys want to take a break, and the next talk starts at 5. Thanks.